Hi everyone, I'm Mathilde and today I'm going to present our paper Location-Aware Self-Supervised Transformers for Semantic Segmentation. Semantic segmentation is the task of predicting the category of each pixel in an image. So the annotations required for this task are extremely costly to acquire. Hence, pretraining is a critical step to improve models on a task like semantic segmentation. However, the prominent methods for pretraining neural networks use image-level objectives. For example, image classification, as in the standard ImageNet pretraining, or image-text contrastive alignment, as in CLIP. And so our hypothesis for this work is that this strategy of image-level objectives is suboptimal for semantic segmentation transfer. And we argue that the reason why pretraining is usually done with image-level objectives rather than pixel-level objectives is because large pretraining datasets are much easier to collect at the image level rather than at the pixel level. And hence, image level datasets are typically 500 times bigger than pixel level datasets. So what we propose in this work is to rely on self-supervision. It means that we want to have a pretraining method that don't use any annotations. And so we want this self-supervised pretraining method to encourage strong features for semantic segmentation. So we propose the LOCA method, and here we're going to consider two views for each of the images in the batch. So one view which we call the reference view, and another view which we call the query view. And we're going to predict different patch level targets from this query view, and these patch level targets are defined from the reference view. So we predict two types of targets. The first type is the cluster ID, and so here we simply adapt self-supervised image level methods like Dino, Deep Cluster, Suave at the patch level instead of their original formulation at the image level. So we cluster the VIT patch features, and then the query needs to predict the cluster assignment of this corresponding patch within the reference view. Then the second type of patch level target is position targets. And so here we simply ask the query to locate itself with respect to the reference view. So in the following, I'm going to focus more on this position prediction task because it's the most novel part of our work. So here's the focus on the position prediction task. So again, we have the query and the reference view. And remember that the task of the query is to locate itself within the reference view. So we implement this as a patch, as a per patch classification loss, where each patch needs to predict the position, its corresponding position in the reference view. So we encode both query and reference views with a VIT encoder, and then the query can look at the patch features of the reference view with a cross-attention module. And so what we find in our experiments is that actually the model is very good at solving this task, and it gets almost 100% accuracy. So we found a way to control the difficulty of this pretraining task. So what we did is to mask some patches in the reference view that the query can attend to. So it means that the query has only a limited access to the reference view in order to locate itself. So let's look at the effect of this masking. So here on the left, we look at different queries, and on the right at different references. And in blue, we show the ground truth location of the query in the reference view. And in red, we look at the prediction of the model regarding the position of the query in the reference view. And so what we observe is that without any masking, in almost 100% of the time, the model manages to correctly find the position of the query in the reference view. So there are just a few cases, so here illustrated by the case at the bottom, where the query is not well located in the reference view, but it's because there is no queue in the query that allows it to localize it in the reference view, and in this case the prediction is completely degenerated. And so here on the left we show the performance when we transfer the network on semantic segmentation with end-to-end fine-tuning, and so we use the AD20K dataset. And so now let's see what happens when we mask 80% of the patches of the reference view visible to the query view. So what we observe is that the performance on semantic segmentation increases significantly. And now we see that in some cases, the model is not able anymore to locate the query in the reference view. But when it does, when it manages to predict the position of the query in the reference view, it means that it relies on the relative position of object parts in the image. So for example, in the second row, we see that the network manages to position the nose of the dog by looking only at the ears. And our hypothesis is that it's because the network has understood the concept, has learned about the concepts of nose, of dog, and of ears, and just by looking at the position of the ear, it can infer where the nose is located. And interestingly, we found that when we actually mask the entire reference view, and in this case it means that the query cannot see the reference view at all, we still get reasonable performance on semantic segmentation transfer. And actually, in some of the cases, the network is able to locate the position of the query in the reference view, even though it does not have access to the reference view. And so our hypothesis is that this is because the network has learned the biases of the dataset and the biases in the way that we take images in our dataset. And in other words, it just learned where things are typically located in images. So for example, in the first row, we see that in this query, we can see a piece of sky, a piece of grass, and so the network can infer that it's most likely located in the middle of the image. And because it's the bottom, like an extremity of the horse, it's either located on one side or the other of the image. And so we found that in some reasonable percentage of the case, the network actually manages to make a valid prediction for the location of the query. So here are some quantitative evaluation on 11 semantic segmentation benchmarks, and we compare our LOCA method with different self-supervised algorithms, so either with dense objectives or image level objectives. And we do so with two architectures, so vid small and vid base. And we see that across the board, our method, LOCA, improves previous numbers on these semantic segmentation benchmarks. So in the paper, we also show that our method improves on this method on the depth estimation, and also improves over image level supervised algorithm like image classification or clip. So in conclusion, we find in our paper that localization is a good self-supervised pretraining task that encourages spatial reasoning, and it transfers well to semantic segmentation and depth estimation tasks. So a limitation of our work is that by optimizing the performance on dense tasks, we've lost a bit of performance on image level downstream tasks. And so here we think that our LOCA framework could be combined with an image level objective to have the best of both worlds. And so actually in the Dino V2 work, what they do is that they combine an image level objective, so Dino, with a patch level objective, which is very similar to iBot. But as we found in our experiments that LOCA is performing better than iBot when transferred to semantic segmentation, one thing that we could try could be to replace iBot within the Dino V2 framework with LOCA. So thanks a lot for your attention, and I invite you to check out our poster at the conference.